point, we've talked about separable equations, linear equations, and exact equations. And you'll notice up here that this example I've written down is none of those at the moment. If I write this in a dy dx form, I can't write a function of y dy dx equals x. Notice if I take the partial derivative with respect to x here, I get y. And with respect to y here, I get 2y. Those aren't the same, so it's not exact. And it's certainly not linear because I've got this y squared term floating around. So at the moment, we don't have a trick to solve this yet. But one of the primary strategies in applied math is bullying hard problems to look like easier problems you already know how to solve. And substitution is one way that we can do that for this problem. By the way, this is very similar to the type of substitution you may have seen in your Calculus 1 class when trying to integrate. Essentially what I'm going to do is I'm going to take some new variable. I'm going to make a new variable up. I'll call it u for that consistency here. And I want to pick u to be some function of x and y that is strategic for me. Turns out for this problem, I want it to be x over y. I want to make. Or equivalently, that means that x is equal to u times y. Now, what does this do for me? Well, certainly I could write u times y everywhere I see an x, and I want to do that, but I think the differentials are the more confusing part here. Notice that this tells me dx is equal to, by the product rule over here, derivative of the first times the second plus derivative of the second times the first, or differentials, I should say. Now I have all the information I need to fully transform this equation, and let's see what happens here. Well, I have x, which I now know is called uy, times y, dy, plus 4 times what I'm calling x now is uy squared plus y squared times dx, which I now know is du times y plus u times dy equals 0. And now we're going to do some cleaning up. Let's make this look a little nicer. And voila, here is some algebra done. So what I did here was I distributed all of my terms, and then I factored out I combined my like terms, I suppose, everything with a dy in it, and everything with a du in it, and here's what I got. And then I noticed, wouldn't you know it, this is separable now. I can separate my y's and u's. And through this substitution, what we did is we turned this differential equation we didn't have a trick to solve into this differential equation, which we do have tricks to solve. And that gives me this solution here, that natural log of y is equal to natural log of the fourth root of u squared times 1 plus 2u squared. But this solution would still be in sort of bad form because we're trying to find a function y of x, not of u. So how do we get there? You guessed it, more algebra. Stay tuned. Well, here we are, solving this equation for y. I first plugged x and y back in for u, right? Remember, u was x over y, so I plugged that back in, and then I've isolated y from that equation. And you'll notice I have solutions of this form. Last thing I need to do is apply that initial condition that we were given. Let's do that. I know that when I plug in 2, here I get plus or minus 2 root c over 16 minus 2, but my initial condition tells me that that should equal -7. After more algebra, this tells us that c is actually equal to 228. That said, my solution to the system is that y is equal to plus or minus absolute value of x times the square root of 228 over 16, or excuse me, x to the fourth, minus 2.